So today we're going to discuss the operational amplifier, or the op-amp. So let's start with the circuit schematic. The basic circuit schematic that you'll see a lot is the following. So you have a triangle with two inputs. One is labeled positive, one is labeled negative, and one output voltage, V out. So we have two input voltages, V plus and V minus, and one output voltage, V out. So this is the basic symbol that you often see for the op-amp. But it's important to realize that the op-amp is a powered device, so we need to connect it to a power supply. So we'll label those for historical reasons VDD and VSS. So this is the largest voltage, this is the smallest voltage, and it turns out because it's a power device that the output voltage will be limited between VDD and VSS. Now for our class, in all the labs that we do, we'll use the highest voltage to be 5 volts and the lowest voltage to be ground. So in our class, our output voltages will be limited between 0 and 5 volts. Now again, this is not a general result. It depends a lot on the particular actual chip that you use, what this power supply voltage will be, and it depends somewhat on your choice as well. So this is not general, but this is our choice that we'll just use 0 and 5. And just for simplicity in all the diagrams I show, we'll just sort of limit things between 0 and 5. Now an actual op-amp looks like the following. So here's our breadboard. So an actual op-amp looks like the following. Here's our breadboard. This is the chip here in the middle. This is our power supply connector that we discussed earlier. So this particular chip is a quad op-amp, which means there's actually 4 of these little triangle-y things on this one chip. So if you count, there's actually 14 pins. So 2 of them are used for power. They'll be the ones in the middle. So the middle pins will be this 5 and 0 volts, which we power the entire chip with. And that leaves us with 4 sets of 3 op-amps. So there's one in this corner, one in this corner, one in this corner, one in this corner. Now this is just a particular chip I'm showing you that it is a quad, so there's 4 op-amps on one chip. They come in different packages, but this is the one we'll use. So it looks like this little black chip, but in the circuit schematic it looks like the following simple triangle, 2 inputs, 1 output. And sometimes we'll be lazy and not draw the power, but it's always important to remember that the chip is powered, and therefore our output voltage is limited between 0 and 5 volts. So it's important to realize that op-amps are designed and made by humans, so they're not fundamental circuit elements, but they're things that have been designed and built for a particular function. Inside the op-amp, in that little chip you saw, is lots of resistors and capacitors and transistors, which is a component that we haven't talked about. This is a schematic diagram of an old op-amp, so it's actually quite simple. A modern one could be, or an expensive one could be much more complicated than this, but you can see there's many little components inside. And we're not going to worry about what's inside it, but what the function is. But it's important to remember that the function, it's not some fundamental thing that was given to us by nature, but these are just simply human-made and human-designed devices to have the particular functions that they have. And then we'll see why they have those functions, because it makes them quite useful for a number of applications. So the first function that we should be familiar with is that the op-amp is designed so the current on the positive and the negative inputs is basically 0. And I say about 0 because maybe it's not identically 0, but it's really close to 0. The particular brand we'll use is the LMC 6484. And if you look on the specification sheet, you'll see about the I plus or I minus might be about 20 femtoamps, which is 10 to the minus 15 amps, which is really small. And while the inputs have no current, the output is able to have current going in or out of the device. It can usually go either way. And the amount that it's limited to is limited by the particular brand or style of op-amp that you've chosen. The one we'll use, the output current, is limited to something around 30 milliamps. So you can buy ones that can provide a higher current, but it's important to remember that current can come out of the device or go into the device, so it can go in either direction. And again, the fact that the currents on the inputs are 0 is just simply something that the device was designed to have. That's a feature that the device was designed to have. Rule number 2, or behavior number 2 of the output, is the following. So let's build the following circuit. And now here the limits are going to be important, so I'm going to put the 5 volts and the 0 as our supply voltage. So I'm going to build the following circuit, and I'm just going to test what happens. I'm going to supply the op-amp with 5 volts. I'm going to hold V minus to be 2.5 volts, so that's going to be fixed. V plus I'm going to control, and I'm going to monitor V out. And specifically, V plus I'm just going to do is a simple ramp. And the range is going to go from 0 to 5 volts. And I'll just go up and down, and I'll do it relatively slow. So the time of each ramp will be something on the order of 1 second. So relatively slow. So I'm going to slowly ramp the voltage up, slowly ramp it down, slowly ramp it up, slowly ramp it down. Now remember, in circuits, 1 second is really, really slow. And then I'm going to generate the following plot. So rather than plotting the voltage as a function of time, I'm going to plot the output voltage as a function of the input voltage, or specifically V+. V+ is limited to 5 volts and 0. And another important voltage is 2.5, which is the one that we've set V- to, which is right in the middle. Likewise, we know that V out has to be somewhere between 0 and 5 because that's the voltage that we supplied it. And if we do this experiment, in fact we'll do it in class, what we'd observe is the following, is that we get a curve that looks like this. So in time, on the up part of the ramp here, V out is at 0, then it jumps up to 5, and then it's 5. And on the down part of the ramp, it just goes back, jumps down, and then goes back. So in this particular configuration, there's apparently only 2 voltages, 5 and 0. However, if we get out our magnifying glass and we sort of zoom in on this region here, so we're considering the same circuit, so let me just redraw it to remind us of the situation. And we're going to have the exact same diagram that we just had, except we're going to zoom in a little bit. So my axis for V out is going to range from 0 to 5. And my axis for V+, I'm going to center at 2.5. However, I'm going to zoom in from before. So here is 2.4999, and here is 2.5001. Something like that. The exact range doesn't matter, other than it's very, very narrow around 2.5. And if we created the same graph, rather than having a discontinuous jump from 0 to 5 volts as we pass through 2.5, what we'd observe is we have 0 down here. We'd have 5 up here, but it would continuously go from 0 to 5 in this range. And so we would find that V out can actually be values other than 0 to 5, but we have to zoom in very, very close to 2.5. And so out here, when we're at 5 volts, all we can say is that V+ is greater than 2.5. And this exact number here depends on the op amp, and actually it's so small it would be nearly impossible to actually measure what this range is. And down here, when we're stuck at 0, when V out is stuck at 0, we can say that V+ is less than 2.5. And if we're anywhere in here, meaning that if we measure V out, and it's between 0 and 5, and again, remember the 0 and 5 are sort of arbitrary. That's the power supply we're talking about. These could be different numbers, but essentially when it's between the 2 rails of the op amp, then what that means is if we're in this region, that V+ is equal to 2.5 volts. And that's the important fact of the op amp. And just to generalize this a little bit more, if I come and I hold this at 1 volt, and I repeat the same experiment, here's 1 volt. So if I do the same experiment where V+ in time, I'm ramping up and down at some slow rate between 0 and 5 volts, and I measure V out, and I plot V out versus V+. When I hold it at 1 volt, I measure the following curve. So as I increase V+, I follow a path that looks like that, and I increase it and I decrease it and I follow that path. If I come and say, for example, remove this and now put it at 4 volts on my graph, what I measure, that's at 0, even though it doesn't look like it, and it pops up to 5, and it goes along that path. And as I decrease V+, then I do this path. And again, just as with when we talked about 2.5 volts, if I zoom in around here, I would actually find some very, very steep slope in there. And so this allows us to sort of generalize our rules from the following graphs. And so what we find is the following. If we measure V out being 5 volts, or our positive voltage rail, all we can say is that V+ is greater than V-. If V out is equal to 0, or our negative voltage rail, we can say that V+ is less than V-. And if we measure that V out is anything other than 0 or 5, our 2 voltage rails, then we can say that V+ is equal to V-. And so this is very important, and we will use this to analyze the circuits that we build with op amps in a very simple way. Behavior number 3 is as follows. So let's imagine the following case. I'm going to hold V minus constant in time at 2.5 volts, so right between our two rails of 0 and 5 volts. Now I'm going to take V plus and I'm going to just put in a square wave. So I'm going to start at 0, I'm going to pull it up instantly to 5, and then I'm going to hold it there for a while, and then I can repeat and pull it up and down. But let's just focus in on the time right around when we do this switch. Now, normally if we followed our rules, we'd say, okay, well, in this state, when V plus is less than V minus, the output should be at 0, and in this state, when it's above V minus, it should switch up to 5. And that's in fact what we observe. But what we observe if we zoom in time is the following, which is that it takes time to change state. Now that time is very short. It might be something on the order of a microsecond, or 10 to the minus 6 seconds. So it's a very, very rapid transition, but it's important that it takes time for it to change state. And that's something we'll come back to in a little bit when we talk about why the circuits that we build are stable. So let's summarize our observations. The first observation was that the input currents are 0. So any current going into these inputs by design of the device is 0. The next observation is that if our output voltage is anywhere between our rails, so 0 and 5 volts, then V plus is equal to V minus. The third observation, we'll just state simply, is that in reality it actually takes time for V out to change. So now let's look at a few applications. So let's look at the simplest circuit we can build with an op-amp that's actually useful. So the circuit is as follows. We simply take a wire and we connect the output to the negative input. We set the voltage coming into the positive terminal of our input is called Vn, and we just simply monitor the output coming out of the op-amp. Our first rule we talked about was that the input currents were equal to 0. So there's no current on this wire, and there's no current on that wire, which doesn't really seem to do much for now. Our second rule was that if our output voltage was anything other than saturated at 0 or 5 volts, then V plus equals to V minus. But in this case, V minus is the same as V out because it's on the same wire, and V plus is V in, so we've built a circuit that simply copies the voltage. V out is equal to V in. So this might seem like kind of a useless circuit, but it's actually not. It's one we'll actually use quite a bit, because you can imagine, say I have some circuit over here, I'll call it circuit number 1, and it's full of things like resistors and capacitors. And then I'm going to connect that, because I need to, for some application, to circuit number 2, which is also going to be full of resistors and capacitors. What's useful about this circuit is that since V out is equal to V in, I can just copy the voltage from circuit number 1 to circuit number 2. However, since there's no current in here, there's no coupling between the circuit. Whatever goes on over here is isolated from what's happening here. It can't sort of back propagate and influence what's going on. No current goes here, so we just have a measurement of V in, and then we copy it and we supply that voltage here into circuit number 2. So this is called a voltage follower, and we'll use it quite a bit. Just simply isolate one part of a circuit from another. All right, let's try something a little bit harder with some resistors in it. Okay, so we're going to have the following circuit with 2 resistors connected as follows. So now let's apply our rules. So the first rule tells us the current on that wire is 0, so we don't have to worry about the current on that wire. So whatever current flows through resistor 1, none goes that way. So it's the same current that flows through resistor 2. So the current through those 2 resistors is the same. So we'll call that current I1, that current I2. I1 is equal to I2. Our second rule is that if this circuit is doing anything interesting, right, so if V out is between 0 and 5 volts, then these 2 inputs are equal. So whatever voltage we have here on the positive is also equal to the voltage there. So Vn, by our second rule, is copied here. So we have Vn at the point between those 2 resistors. Now we're at the point we can just apply Ohm's law, right? Because now I know how to find the current through resistor 1. We have V out minus Vn over R1, and that's equal to the current. but that's the same current that's going through this one. So that's equal to Vn minus 0 over R2. And so now I can rearrange this to get a relationship between V out and Vn. So I can say, just multiply over by R1, move the Vn over there. Vn plus R1 over R2 times Vn, or V out is equal to 1 plus R1 over R2 times Vn. And so this is an amplifier because whatever voltage we get out is equal to Vn but times some constant factor. So if I make R1 bigger than R2, then I can get a large amplification or gain of this circuit. So this is a simple amplifier. A modification of the circuit that we'll often use is that rather than connecting this point to ground, we'll connect it to Vref. Again, I'll put my power supply in there. So since no current can flow on this wire by our first rule, then our current here and our current here must be the same because whatever current flows into this node has to keep flowing there. So there's only one current. And again, by our second rule, if this circuit is doing anything interesting at all, meaning that V out is not 0 or 5, it's between 0 and 5, then our two inputs have to be equal. So whatever voltage I'm putting in here is copied here, and that becomes Vn. And so again, this circuit is quite simple to analyze. Since we just use Ohm's law, we say that I1 equals I2 is equal to I, so the current through that resistor equals the current through that resistor. The current through resistor 1 is V out minus Vn over R, and that has to equal the current through resistor 2, which is Vn minus Vref over R2. Now I can rearrange this in the same way that I did before, and I get the exact same result that I got in the previous circuit, except now it's a difference. So it's Vn minus Vref multiplied by our constant factor equals V out by minus Vref. So this circuit is exactly the same as when we connected Vref to ground, other than now Vref is not 0. And so therefore there's a constant offset that we can easily introduce into our circuit. Another related circuit is the following. So the first rule is that there's no current on the inputs, which doesn't seem to matter down here. But here, this current I minus will equal to 0. Whatever current flows through resistor 1 has to flow through resistor 2, because in terms of current flow, nothing happens here. Our second rule is that if V out is anywhere between 0 and 5, then this point here will be at 0. So we can use our same rules as before. I'll call the current flowing through here I1, the current flowing through here I2. But our first rule, since there's no current there on that input, I1 is equal to I2 is equal to just the single current I. We'll apply Ohm's law to this resistor here, so that current equals Vn minus 0 over R1. And that same current has to equal 0 minus V out, because I drew the arrow in that direction, over R2. So that means that V out is equal to minus Vn times R1 over R2. So this is also an amplifier, except that it changes the sign. Now you might notice a problem with this, which is that if Vn was something like 1 volt, and these two resistors were, let's just say they're equal, so their ratio is 1, V out would need to be negative 1 volt, but this circuit can't put out a negative voltage. It can only put out something between 0 and 5. So you have to be a little bit careful with this circuit because it's changing the sign. It's an inverting amplifier. One simple correction to this, or one simple modification of this circuit, is just as in the previous one. We can do exactly the same thing, except we connect this point here, V plus, to our 2.5 volts. But the analysis is exactly the same. There's only this current flowing through here. And if this is connected to nothing, then the current would be going into the op amp. So the current flows through this resistor, through that resistor, and into the op amp. By our second rule, if this thing is anywhere between 0 and 5 volts, the voltage there better be 2.5. And so therefore we can analyze the circuit in the same way. We can say the current flowing through this resistor is Vn minus 2.5 divided by R1. And the current flowing through this resistor is the voltage across it, 2.5 minus V out over R2. Or V out minus 2.5 is equal to R2 over R1 times V in minus 2.5 with a negative sign. So what this means is the following. If I had some circuit that was giving out something close to 2.5 volts, but let's say it's looking like this, so a little sine wave kind of fluctuating up and down about 2.5 volts, and that's V in. V out, depending upon this ratio of resistors, would change sign and be larger, but it'd be relative to 2.5, so everything is subtracted off 2.5. So this circuit is an inverting amplifier with an offset of 2.5 volts, which is set by this point right there. So we have the following scenario. So I'm going to just take my op amp, I'm going to plug this at 0 volts, I'm going to plug this at 1 volt, and I'm going to monitor the output. So the x-axis will be time, this will be voltage, here will be 5, 0. And so now this voltage here, V plus, is at 1, which is right down here. And I'm just going to hold that constant for all eternity, so that just goes straight along in time. Now, V out, when we're in this configuration, 1 is greater than 0, so V out will equal to 5 volts. And so it's going along at 5 volts, and V minus is at 0, so it's going along at 0. So nice and boring. Except, right here, at this time, I'm going to do some magic. And what I'm going to do is I'm going to imagine that I could instantly, with lightning speed, yank this wire out and connect it like that, so that V out and V minus become one and the same. And since there's an op amp here and the op amp takes time to change state, V out stays at 5 volts. And so V minus jumps up by magic because I'm so fast. And now V out and V minus become one and the same. So now I'll just write V out in the purple because the blue and the red have merged. Now, it takes time, remember, for the op amp to change state. So now we have 1 is less than V minus, right, because this is up at 5 volts. And so that's going to want to make the op amp change state and become negative, right, because now V plus and V minus are not equal. And this one is greater, V minus is greater, so it's going to want to go to 0. But it can't do it instantaneously, so it starts decreasing. So it starts going down, 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 down. And what would happen is once it crosses 1, then this voltage V plus is greater than V minus, and so it's going to want to increase. However, when it crosses, it's going to want to decrease. And so there's a stabilization effect because this is connected to, the output is connected to the input through the negative wire. Now in reality, this is not what we actually measure, but we do measure something quite similar. And so what we really measure is something that looks more like an exponential growth, or an exponential decay towards 1. And we'll explain a little bit in a later video why it looks that way. But this is what you really measure, not that. But the concept is the same as I explained. And now it depends on the exact op amp, but this is something like 1 microsecond that this time scale will happen. So very, very rapidly converge to this time scale, but it does it stably because it's connected to the negative input. Now, if we went through the same exercise, however, if we reverse the situation, so I start off, this was at 0, this held at 1 volt, this at V out, and I can instantly now pull that wire out and make that connection. By the same arguments we just made, we would find out that this is unstable. And that it's not stable in this configuration. So with positive feedback, it's unstable. With negative feedback, it's stable. So our summary is very simple. So we have a couple of rules for analyzing op amp circuits. So our first is that the input draws no current. The second is if our circuit's doing anything interesting at all, so the output is somewhere between 0 and 5, then our input voltages we consider to be equal. And the final is that negative feedback is required for the circuit to be stable. And by negative feedback, I mean there's some path, but it could be through some circuit elements, but there's some path from the output back to the negative input. So that's the summary. We'll do more applications in class and in some of the later videos as well.